Hi, my name is Dheeraj Chahal and I'm scientist with the Computing System Research Lab at TCS. Today I'll be talking about our work on performance and cost comparison of cloud services for deep learning workloads. Specifically, I'll be talking about ML platform and serverless architecture offered by AWS. My co-authors in this work are Mayank Mishra, Surya Palepu, and Rekha Singhal. This is how I have planned my talk. I'll start with the motivation behind this work and then we'll discuss the objective. I'll walk you through the ML platform and the serverless architecture, followed by our strategy for migrating the workload to these two cloud services. We have done some experiments for cost and performance comparison of cloud instances and services that we'll discuss before we conclude. We all know that when it comes to deep learning model inference in real time, there are very stringent performance requirements as defined in the service level agreements, such as the minimum throughput expected and the maximum allowed latency requirements. So to achieve and to honor these SLAs, organizations invest upfront and develop high performance clusters which are sometimes economically non-viable. And one solution to this is to migrate your workloads to cloud services that offer you the cloud infrastructure and it is very cost effective. Many cloud vendors provide services for migrating AI workloads to cloud. For example, Amazon EC2 and Google App Engine web frameworks. Some of these vendors provide fully managed AI cloud platforms as well. For example, SageMaker AWS, Azure ML by Microsoft, and Google AI platform. These platforms help in minimizing the AI migration efforts. Serverless architecture is also emerging as a paradigm of choice for migrating AI workloads. AWS Lambda is one such serverless platform offered by Amazon. Platform and serverless platform provide many advantages over on-prem deployment. For example, scalability on demand using auto-scaling features available on these platforms. It's very cost effective as the user is billed based on the time for which the service is used. It also provides location and device independence. User has freedom to choose either CPU or GPU based devices and they can be deployed over multiple geographies. It also provides ease of deployment using frameworks and APIs that are available with these platforms. Likewise, in serverless platform as well, it is cost effective. It provides highly scalable architecture, and additionally, there is minimum operational logic required in serverless platform so that user need not worry about the execution environment. There are certain limitations of serverless architecture. For example, maximum memory available is 10 GB. Maximum storage available is 500 MB, which includes 250 MB for deployment packages. Also, the total number of cores available are limited by memory reserved with the serverless instance. For example, with 10 GB, there are maximum 6 cores available. Most importantly, there is latency because of the cold start, and cold start is due to the time spent in preparing the execution environment when the first request arrives. So with this context, objective of this work is to implement a scheme for migrating a deep learning based recommender system to cloud and to study the performance and cost involved in DL modern inferencing with different types of instances that are available on cloud. We have also focused on performance and cost comparison when a recommender system is deployed using ML platform SageMaker and serverless platform AWS Lambda. So in this study, we have used homegrown recommender system called Nicer as a use case. Nicer is based on GNN. It's a session-based recommender system which uses only the recent actions of users for recommendation. And items in Nicer are represented as embedding. Also for prediction, the sequence of items in the current session is used to find the top key items for next recommendation. We have used SageMaker APIs to deploy the recommender system. A call to fit API internally invokes train function where user has defined the training code. Train function downloads the training data from S3, and once the training is completed, model is saved back on S3. A call to deploy invokes model underscore fn, which loads and deploys the model on the endpoint server along with the configuration files. Prediction is made using the prediction API, and once the prediction job is over, endpoints are deleted using endpoint delete API. So this chart over here shows the recommender system deployment on AWS SageMaker and AWS Lambda. The training data is loaded onto S3 storage, and we run the training jobs on one of the SageMaker instances. Once the training is over and the model is ready, it is saved back on S3, and during the deployment the same model is taken from S3 and deployed on one of the SageMaker instances. So we are using both CPU and GPU type of instances for deploying the model. Prediction requests are sent from Jupyter Notebook, and then results are returned back to the same instance. While for AWS Lambda, we save the model on S3, and once the first request arrives, this model is loaded into the memory of AWS Lambda along with other packages. One important thing to note here is that there are limitations on AWS Lambda memory size, which is maximum 10 GB available, and also there are limitations on the storage, which is 500 MB. So for deployment of PyTorch, which is 900 MB in size, we have to reduce the size by using only the CPU version of PyTorch. So that size reduces from 900 MB to 200 MB, and it's easy to load that 200 MB from storage to memory. So let's talk about some of the experimental results now. In this particular experiment, we use three different types of SageMaker CPU instances: X large with 4 cores, 2X large with 8 cores, and then 2 instances of X large. So what we see here is, as we increase the capacity from X large to 2X large, we see a drop in response time, which is according to our expectations. But there are two interesting things to note here. One, that 2 instances of X large with 4 core each are giving us better response time in comparison to one instance of 2X large, which has same number of cores, that is 8. And another interesting thing is that in case of 2X large, cost is 2 times that of X large, but the performance gain is hardly 1.3x. We repeated the same experiment but with SageMaker GPU instances. What we see is we get significant improvement in response time when we migrate from CPU instance to GPU instance. But across GPU instances, behavior was same as observed with the CPU instances and discussed in the previous slide. Interesting observation that we see in last two experiments with SageMaker CPU and GPU instances is that while using multiple CPU and GPU instances instead of using one instance of similar configuration, there is a large variation in the response time for the request, especially at the higher concurrency levels. This is primarily due to the load imbalance happening on SageMaker model server at higher concurrencies. This graph shows the comparison of response time observed with on-prem CPU, SageMaker CPU and GPU endpoint server, and AWS Lambda. At very low concurrency, we observe that response time from Lambda is higher than SageMaker CPU and GPU. This is due to the fact that the compute resources of CPU and GPU instances in SageMaker are underutilized. As the concurrency or load increases, resources are saturated in SageMaker instances. However, Lambda provides high scalability and spawns instances proportional to the number of requests. This results in a constant response time in Lambda, but it increases linearly with increasing concurrency in SageMaker CPU and GPU endpoints as well. As shown, the response time observed with CPU endpoint is highest as compared to GPU endpoint and Lambda at higher concurrency values. Although activating scaling feature in SageMaker can mitigate the increasing response time problem, but the result is that higher implementation cost as compared to pay-per-use model used in Lambda. We also observed that response time for on-prem deployment is higher as compared to SageMaker CPU deployment with comparable configuration. This is due to the optimized libraries and environment used in SageMaker. SageMaker and Lambda have unique cost model and hence are challenging to compare. The cost of SageMaker instance is proportional to the uptime of the instances and it is independent of CPU usage, whereas Lambda follows pay-per-use model that derives cost based on the total execution time, memory used, and the number of requests served. On the right-hand side, we see the maximum achievable request rate for each instance and its fixed cost for 1 hour. However, Lambda cost is shown in the figure is dependent on the request served and the time for serving those requests. The intersection point of Lambda trend line with each of the instances represents the break-even point. If the request rate extracted from the instance is below the intersection point, serverless is a cheaper option. This is due to the fact that SageMaker instances are underutilized in this stipulated 1 hour, but billed for the whole duration. However, if a request rate extracted from an instance is between the intersection point and maximum achievable, then SageMaker is cheaper because instances are optimally utilized. Based on these experiments, we can conclude that there are some scenarios where serverless architecture delivers better performance due to fast and high scalability for busty workloads as compared to the ML platform. On the other hand, ML platform is better option for long-running workloads where resources are optimally used. So in this work, we have presented a performance and cost comparison between different types of CPU and GPU instances when used as SageMaker endpoints. Also, with the help of these experiments, we can conclude that the additional cost that we see in the scaling of ML platform instances does not mean a proportional increase in the performance. And the auto scaling in serverless architecture results in better performance when compared with the dedicated SageMaker endpoints like CPU or GPU. There are certain scenarios where serverless architecture delivers better performance due to its high scalable architecture for busty workloads as compared to the ML platform. Thank you for your attention. For further queries, you can reach author at d.chahal@tcs.com. Thank you very much.